Cool. Okay, good. Okay, let's start. Oh, wait, let's start. Uh, in the last class, uh, I forgot to mention this self operating system. It's important. It's very important now. Eh? Why it's not playing? Eh? Okay, let's try. Why is it cannot play? Record is group. Uh, how can I play this? Oh, sorry, I cannot play this. I add this uh called record group. Oh, sorry. Okay, I figured this out. I said it cannot play on this slides, so we can play next time. So let's directly go to the chapter 2. Okay. Okay, chapter 2. Now in this last class we have an introduction about the operating system, and we know it's very important. And from this class, we're going to the details. So this is operating system and service. And from now, I suppose you not miss my class. Once you miss this class, I suppose you cannot follow in the next class. It's a logic. It's a logic chain, logic by logic. Okay. So we know from last class, operating system provide some of a user interface like a UI and the programming extraction, IO file system and communication error handling. Let's say the one of the important for operating system is resource allocation, like CPU cycles. We have thousands of process. We have thousands of processors, but our laptop may only have a 6 core, 16 core, 16 core. And we have thousands of processors that need CPU cycling to manage this resource. Main memory, file storage, the I/O device. Logging the is record the events that happened in the OS and the protection and securities. Okay, this is I like this diagram. I say this is important. This diagram is to show the structure of the whole operating system. Say this is the user. This is the user space. We always say all user mode. This is the kernel mode. And between the user mode and the kernel mode, there's a system call. User mode and the kernel mode is a totally separate, different space. The system call. So in the user mode, we have lots of applications like a user interface, UI. Everything we can say in the OS or in your laptop is UI. UI is GUI, graphic UI, and the touch screen, or cell phone touch screen, and the command line. Everybody use the command line. All of the user interface use the system call to access the kernel mode. This kernel mode is to manage the resource, like manage resource and hardware, like the I/O operations. It's manage the input and output I/O, and the file system is manage the hardware of a disk file system. Resource allocation. Manage the memory. How can we allocate, delocate the memories? And the protecting security, error handling. All of this service is running in the kernel mode, right? Kernel mode, and here is the hardware. So operating system is an intermediate layer between hardware and user. See, this is hardware, this is user. As our user, can you directly use the hardware? It's possible. It's too hard. It's too hard. And with the operating system, you don't need to care about what kind of CPU you use, AMD, Intel, or ARM. You don't care about that. All the operating system will handle this hardware resource. Okay. I see. Okay. This is I like the diagram. I find it from Wikipedia, and it's more details. What can you see? User mode, kernel mode. The user mode and the kernel mode, and the user mode this is user applications, have lots of applications. Firefox is a browser, and the system components. System components is used by system. Like I know the security is UI, and the C standard libraries. All this is used by application programming. You want to develop an app, you must use the C standard libraries, like open the file, close the file. This provides the C standard libraries, and this kernel mode is a kernel mode as a very specific, like a memory management, IPC, is a process communication, a virtual file, the file system, networking. All this is in the kernel. This Wikipedia provides more details. Okay. Let's say the command line. Everybody use the command line. It's a shell, right? Shell. The command line contains the code to execute the command. We can write a script. This is write a script running on the cell. Let's say an example. So multiple shells that can be available. Yeah, we can run multiple shells. So this equal 0 or equal shell will return the current shell you are using. So we have lots of different shells. The operating system, the shell is just the application of the operating system. We have lots of different shells. We can use the equal 0 or equal shell to return tell us which shell you are using. That's that. Here I use a Mac as the example. I can use the equal shell. Let's tell me this shell is this sh. This is under the directory bin of this sh. So the Mac is running in the cell. And the different of Linux, different version of Linux maybe use a different shell. Okay. And also shell do not have the code to exactly request. So for example, we can use IAM to remove the file, delete the files. So where this IAM come from? This is not come from shell. It's a command line that's loading from it's a command and it's an executable file loading from here. It's directly under directed bin. Bin is always a binary files. This will type this which RM it will return. This RM in the shell will execute which program. This one. Okay, the shell don't include any kind of implementation of the RM. The shell is just a command line UI. Command line UI. Okay. Try in your local if you have a laptop. Okay, this is the more of command line. We can see this. After time, they can show the time. DS, this will show the disk files. DS. So the disk file system. And this PS will show all of the process that is running, all of the process that's running on the OS, PS. And the LS, we always use this, LS, so show the directories, LS. Okay, this is all from a command line. This is the kind of UI from a command line. And this is very used. I know this is hard to learn at the beginning. We must remember all of the command line, df, ls. But it's very used for script, automatic execution in the server. Right. Here, system call. Just now we talk about the system call is the layer between the user space and the kernel space, user mode and kernel mode. User mode and kernel mode, remember, is totally different. They cannot directly communicate with each other. They must use the system call. So it's accessible by programs via a high-level application programming interface. We always call the API rather than directly system call user. Or in our programming, we always use the API, not directly use the system call. Later, I can show you some examples. Okay. API is a set of interface function available on the programmer. So the operating system provides you API. So this API may implement with the system call. And our application programmer do not care about the details of the system call. Okay? We have three most common APIs. Where everybody uses Windows, it's Windows. And Windows Win32 and POSIX API. POSIX is the Linux standard. So all the Linux or like Linux system, like Unix, Linux, like the Mac OS, like the Solaris of the Sun. Solaris, they are a Unix-like or Unix-like system. They all use the POSIX API. API is the same API, but implementation may be different on different operating system. And also the Java. Java is also widely used in the commercial applications, Java. So Java has its API for its virtual machine. We know Java is running on a virtual machine. And Java is not directly running on the hardware. It has a GVM, the virtual machine. Okay, this system call request to copy the contents to one file to another file. Okay, this is the whole process of copy the file. We have the source file, we have a desktop file, and the source file we will execute a system call sequence. Execute the system call sequence, acquire the input name, and write the prompt to a screen. Access the input, acquire output name, write from the screen, accept the input. So then open the input file. If it doesn't exist, abort. It has many details. If the file does not exist, how can we handle these errors? Let the operating system handle these errors. And create output files. As a loop, as a reading, and then close out the file. Write complement message to screen, terminate normally. Right? And this is an example of standard API. Standard API. This is read. This is the function read. It will read the file. Read the file FD. FD is the file descriptor. It's an integer. FD is the file descriptor integer. Read the file into this buffer. You must allocate the memory for this buffer. how large you want to read? How many bytes you want to read? You read the count. So you read the file into the buffer. How many is count? The count. So this and the return the size is the return the value of this the maximum number of bytes to read into the buffer. So this is a standard API. This is used by Linux. It's a Unix-like. It can work in my Mac because my Mac is Mac OS is a Linux-like system. How about Windows? Does Windows have the same one? Windows has the same one? Yeah. Yeah, Windows has the same one?
Probably slightly different.
Yes, different. Because this read is a standard API of operating system. Operating system. Okay. Operating system. In Windows is different. Different. Later we can say an example. So this is system call. Can say this uses this read will trigger a system call because this reader is used in the user space. It will trigger a system call to go into the kernel space. I think I can show you what is the system call. Okay, now I have the source code. Hey, where's my source code? Where's my source code? Okay. Hey, okay, here. Okay, see, this is an example of sorry, sorry. Okay. How can I make this can you see clearly? Okay, now it's large enough. Okay. So this is the Linux system call. It's an operating system related. It can run on my Mac. Say it uses open the file. It uses open the file. All this is error handling. So SD is the integer, right? If SD is a -1, it means that this file does not exist. Error opening the file. Skip this, and we must initialize the buffer. Initialize the buffer, allocate the memory for this buffer, and then we can read, and then we can read, and that is don't forget to close the file. Once you forgot to close, what happened? Nobody will close this file for you. It will cause the memory leaking. This resource is not well managed. This file is still open. Okay, don't forget to close the file. And this is I can run. It will write the file into my computer, and I run. Okay, you see it can run on my Mac. Open successfully. It read 21 bytes as it shows this is the file content. So if you're sitting in the back, can you see clearly my code? Good? Okay, good. This is different. This is different. This code is use C standard libraries. C standard libraries is I don't forgot to discuss that. So this open and close is in this head file. File control.h is provided by Linux. And then this one, F open. This is in the standard libraries, C standard libraries. It's not provided by the operating system. It's provided by C standard libraries. So this is the F open and F gets and F close. If you learn the C programming, you cannot miss this F open, F get and F close. This can run on all of the operating system only if it supports this standard library, glibc. but I see all of the operating systems support this. glibc is widely used standard libraries. glibc. Some of Python, some of language like Python, it use different. I know it's different, but essentially, in the implementation, the Python use glibc to implement this file open and close. So this can run on any kind of system. It's good idea to use this one. Otherwise, if you use the Linux, API, so how about you use Windows? You change to Windows, you must update your API, change to different. Okay, good. Here I not show example of a Windows API. It's rarely used. Okay. This is a simplified source code of read. You know, read is what? Read is what? Read is Linux API, Linux operating system API. So this read will, the implementation is use a system call, system call to go into the kernel mode, kernel mode, right? Here I can show you what is system call. System call must have a number. Like sysread is macro defined. It tells the system call which function you are calling. Yeah, it's the system read, and 3 parameters, the FD, buffer, and count. They must tell the kernel which function you are using. It's the sysread. And later, this system call define is a kernel system call entry. Well, this will trigger going to here. System call define. It's read. This is read. All of this is the parameters. This read will trigger this VFS read. Remember, this is not in the user space. It's in the kernel. It's in the kernel. It will trigger a VFS read. What is the VFS read? VFS is the virtual file system. It's used by Linux. It's a file system. It will use this file system read because in Linux we use the virtual file system, but in Windows don't have. Windows have some NDFS or other kind of file system. Windows don't have virtual file system. So in the Windows, as a different, Windows don't have this. It's a virtual file system read, and this virtual file system read will go into. Oh, this is the virtual file system read. This virtual file system read will go into what's going to read bad. Oh, call read iterators. So this will dispatch. This will dispatch this virtual file system read to hardware because it's in the hard disk or SSD with a weight disk. So which block it will go into this hardware? Call read iterators going to the hardware. Until here is the hardware word. Now here's this code where I just show you what is system call. Okay, here what is system call? System call is a bridge between the user space and kernel space. I always discuss this many times. Okay, any questions here? Good, and here feels good. Okay, let's back to our slides. Oh, slide. So just now I show you an example of system call. Right? How the system call implemented? It's maintain a table. And it's maintain a table to index. I could just it's a number. It's a number to indicate that which system call the user space user. It uses a table to indicate according to this number table. The caller needs to know nothing about how system call is implemented. It just need this API. Just need this API. Okay, this is a user space. Okay, this is a user space application. We have to open the file, right? Open the file, and all of this is in the user mode, and all the other this part is in the kernel mode. Between user mode and kernel mode, this is system call interface. A system call interface. This open will go into system call and go into the kernel. This kernel, it has maintained a table. This table will indicate which system call you are doing. So, and going to here check the table because you do remember the system call function. The first parameter is a number. The number are going to check this table and find that it's a find that is a implement it's a here print here. So it maintain so in the kernel it maintain a table. Oh yeah. Three general methods used to pass the parameter to OS. We can say we have the open function have the three parameters. First is what? FD is the file descriptor. Second is what? Buffer. And third is count. How can we pass these parameters to from a user to kernel? We know it's different space. Simplest way, so we have registers. Register, but the registers has a problem. Register. So CPU only have a limited number of registers. I forgot how many parameters the register support. But if you have more parameters than the registers, it cannot pass. Register can only pass like a 3, because we have only 3 registers dealing with the parameters. If you have more than 3, it's not work. It's not work. Then we can use the memories. We can use the memory. So the parameter is stored in the memory, and it is the memory address will pass passed by the system call. Like I will say, the user space and different kernel space are different space, and the memory space is also different. It cannot directly access the memory. The kernel cannot directly access memory of a user. So that's why passing parameters, we need to store the parameter in the memory and then tell the kernel that, oh, my parameter is stored in this memory. So register is simple. Only supports several parameters, but memory as a parameter is good. The parameters are placed and pushed into the stack. So the parameter in the memory is in a stack, pushed in the stack, and then later popped from the stack. So what is a stack? It's in the class. It's teached in the class of data structure. Who remember what is the stack? What is stack? Hello. Yes, it's the first thing first of structure. We put this parameters to the stack, and when we use it, pop out. Okay, that's the registers. That's a table of registers. It's a system call. We have the parameters, and loading address to the system call, and loading address of a system call. So 30 is the system call index, then going to the kernel. And this parameter is passed by this X is passed by registers. Register, CPU register. It's a fast, simple, but only support one in this case. Only support one parameter. Okay. Until here is good. Oh, see the source code. I already see the source code. Okay. Until here, we know what is system call. And this is the important concept in the operating system. And I say all of the modern system has at least two space, user and mode, user and kernel. And they use a system call to communicate. And they use system call to process control, file management, device management, information maintenance, and communications. Like later we can show examples, protections. All of use system call. Okay. as I say, Windows and Linux, Unix has different OS API. So this is a different API. So for process control, let's say, this is for Windows. The name is also always very long, looks complicated. And Unix, Linux is very elegant and simple. That's why I include programming on Windows. So the name is very long. There is a process control as a create process in the Unix is a fork. Exist process on Unix as exist and wait for this is a wait for single object. Oh, it's a very long name. Four words in the Windows, and it's for wait. It's for process control. And the file management, device management. Later we're gonna discuss this. You can see all of the name is very long. It's I don't know why they designed like this. Good. Okay. This C program invoke printf library call, which call write system call. So this is a implementation of how printf. Everybody know printf. Everyone know printf. It's a print message on the screen, right? How does that happen? How does it happen? It's a standard C library. It's provided by standard C libraries. It's not provided by the OS system. It's a C libraries. In the user space, we use the printf, and then from the C library, calling C library, it's going to the kernel. This kernel will call this write system call to the std out. Write system call. std out is standard output. Standard output is command line. So it is just a write this string to the standard output. In the Linux world, everything is a file. This standard output is also a file. It write this message into this file. But this file is for showing in the screen, standard output. They are here. So every time we use printf, it's actually is process. Okay. So next we have an important concept of linker and loader. Linker and loader. How about the source code? We compile the source code into, in the Linux, we use the GCC to compile, right? We compile the source code to the object files, relocatable object files. And then we link this object file into executable files. And okay, I think cell diagram is better. Okay. I think this code is very simple, right? Who can explain? Okay, explain the code. Yeah. Yeah, very good. Good. The next question is we'll compile this code, what happens? We'll compile this code, what happens? So the source program will compile, we'll use GCC/3, we'll compile into object file, main.o, object file. This main.o will compile to the program of executable main. So /o is our target main, and its main.o is come from here. It come from this file, and it must link what is the LL? It must link a library. Must link a library, and it can generate a main files. So /LL is /L is tell the GCC to link the mass library. This is the format of the Linux. L means link, M means libapp. This is the mass libraries. Without this mass libraries, how can the compiler don't know where you implement the SQRT? The compiler don't know that, right? Because this implementation is in its libraries. And this library also includes some basic mathematical computations like sin, cosine, SQRT. This will link this library to this executable files. If you not include, it will give you a what error. Cannot find the libraries, cannot find the implementation of SQRT. That's where you need a /lm. And other libraries like libthread, this is a library for thread management. And this SQLite. What is SQLite? You know? It's for database. Sometimes use SQLite is a database. Always used in local machines. And if you want to use it, you must include these libraries. Okay. Okay, we know what is libraries. It's better than explain here, right? So we have two different linking, standard linking and dynamic linking. Standard linking and dynamic linking. Just now we are using this is dynamic linking. Dynamic linking creates a compile work at the runtime because this library will called during the running time, not in the compile time. Yeah, know what it means? So the executable is dynamically linked because it contains dynamically linked. It's contains the implementation of some functions, and it's dynamically called. It's not compiled into the files. For example, it's not compiled into the main file. This example file, when you're running it, you need these libraries. And because this is the standard C libraries, so it's every computer has this. It's dynamic link. And the other one is static link. Static link is compiled into the source file. Like this one. So libc.a is and compile to a.order. I would compile this library into this executable file. So this executable file will not need this library when it's running. This is static link. You can use the GCC cell stack to compile this one, to compile this static link, and then running you don't need this libraries. But I tried this, but it's not supported on my Mac OS. It should be supported on the Linux. So Mac OS and still have little difference with the Linux. Right here, dynamic link and static link. Any questions here? This is
Would any one of those be faster at runtime than the other?
Yes, you're right. Because I try to discuss this in our memory. Dynamic links, you see, it has the process of that library is not in the memory. We must load the library from the disk to the memory. Let's make it slower. And for the other benefit is this library may be used not only for this program. It's used for some maybe other process. And it can share the memory. So this libraries can be used by, for example, libc. Libc is a standard C library. It's used by many applications. Why you have so many copies? Why is it enough? This one in the memory is totally enough. It can run in dynamically linked to the program. But you say it's slow. It needs to load in from disk to the memory. But the static link is good. Once the application runs, it loads into the memory, whole into the memory. But this libc maybe have one program have one copy. It's not a good idea because our memory has limited memories. Every process that has a copy of a libc is not a good idea. Good. Implementation. Okay, we talk about lots of OS. Uh, so all early OS in the implemented in the assembly language. It's good because at that time C is not yet developed, not yet invented. So they use a assembly language. After the first Unix is written by C, or they find C is really powerful. And then system programming you have system programming language. I don't know this. It's a very it's old, disappeared. Now we use C and C++ and Rust. You see, all of the kernel code, all of the Linux kernel code is written in C, not C++, is in C. And C++ is very heavy. C++ is lots of libraries or the STL, the standard template. It's a very powerful for applications, but it's too heavy in the kernel. Kernel still uses C. And in Linux, Linux uses Linux C. It's different with some Windows C. Some features are not supported in the Windows. Now it uses Rust. Who knows Rust? Rust. Oh, I should put a logo of Rust because this is a really hard research topic. Rust. No one knows? So when you use C, the biggest problem is what? When you use C, the biggest problem is manage the memory. Memory allocation, delocation. You see, just now, open the file, I forgot to close. Memory management. And the buffer, the memory, you must allocate the memory for the buffer. So that's in C. C is always has this memory management problem, pointers. Your pointers point to other locations. C always has always have bugs and hard to fix. Rust is designed for solve all these bugs during the compile time. Rust don't have like a garbage collection like Java. Rust implemented the garbage collection in the compile time. In the compile time, it's managed the memory. So and the compiler will check is this memory is allocated is delocated correctly. The compiler will check this. That's why the Rust is really popular today. It's really annoying when you're learning Rust. You must fight with the compiler. The compiler always tell you your code is wrong. Your code is wrong. But after you pass the test of the compiler, your code is high quality. Okay, but C is different. The compile is easy. Even the code has some errors or some bugs, it still can compile. The compiler don't tell you. But when it's running, it causes lots of unexpected bugs. Okay, I think next time I put a Rust logo here. So it's really this year it's really popular, and Rust is not easy to learn. Fight with the compiler. Usually, we mix of different languages in modern operating system. The lowest level is assembly. So assembly is still used, but only for some of the parts that's CPU related, hardware related, or what? Or in the high efficiency. For example, the memory copy. The memory copy, we want it very efficient in some hardware. So we can implement that part in the assembly language. And the main body in C. So the Linux in the main body is implemented by C. And some system programs, C and C and C++, like Python and shell script is an application. The application used by the system. This can use C, C++. So on the top applications, you can use Java. I can use C#, right? Java is designed for commercial using. It don't have the memory problems. Automatically use garbage collections. It's efficient because the application not worry too much about its efficiency. If it's much more efficiency related, like a game engine, it still use C++ or C. So emulators that can allow OS to run non-native hardware, so virtual machine. Oh, I guess the lab one you build your virtual machines. This virtual machine is running on the disk. Sorry, running on the laptop. It's a emulators. Okay. System program. System program. They are called system program can be divided into it's a system utility to manage this system. File management status information. We'll go into this details later. System program. Okay. We'll go into the details later. Okay, now we discuss the basic things of operating system. Let's see some examples. The general purpose OS is a very large program. In your laptop, now is Windows 11, and the Mac OS is the general purpose OS because we use it to do lots of things, anything. Some specific OS, like the embedded system, is very small. It must be very small. And various ways to structure the system, the simple structures, like MS-DOS. MS-DOS is already disappeared. Simple structure, more complex than Unix. And layer by layer is abstractions. Abstractions is this modern server system, like iOS. Simple is the monolithic structure. It's a single part. It's because it's very old. It's MS-DOS. At that time, the hardware resource is limited. Hardware resource is limited. So it only has a single part. They more care about efficiency. Hardware resource is limited. More care about efficiency. How can I save the memories? They not care about how can we split the user and the kernel mode. No. So all of the functions like kernel and kernel functions of the kernel, like process, memory, file I/O, is placed into a single static binary file that runs in a single address space. Or we not yet discuss the memory space, so they are in a single address space. Because it is simple to implement, like MS-DOS. MS-DOS, the old operating system implemented like this way. But the original Unix, limited by the hardware function, the Unix operating system had limited structures. The kernel consists of everything below the system call interface and above the physical hardware. Same like the MS-DOS. Not clear of a user, not clear divider for user and mode, user and kernel. And this is the traditional Unix system structures. It's beyond the simple, but not fully layered. It's a little complicated. This is the user space, and this is system call. It's kernel space, and termination control, device control. So it doesn't have a very clear of where the user space. It's early Unix. Early Unix. Okay. This is a monolithic plus modular address. Because this is more clear. This is a modern Linux system doing user application. The user space, it has system call interface. Our application includes glibc, standard libraries. Any Linux has its standard libraries. Okay. And then it has a kernel, it's a device drivers, file system, CPU scheduler, lots of things that is in the kernel. And then the hardware. So now you say it's a modular design. It's a modular design, it's different modules. The file system or network is different modules. It's easy to maintain, not mix them together. The early operating system to mix them together. Now it's layer by layer. This a layered approach, it's different layers. And from layer 1, layer 1 is a layer n. It's divided into number of layers. And each built on the lower layers. And the bottom layers, layer is hardware. This is hardware. The highest is a user interface. It's with the modular layers are selected such that each user function and service for only used for lower layers, for lower level layers used. Okay, mesh. This math is an example of a microkernel. And Mac OS kernel is partly based on the mesh. Mesh is a microkernel system structures, microkernel. And our Linux is a single kernel. You see, the Linux only has one kernel. And but currently user, including the Windows, is a microkernel. See example, see, microkernel system is need the user mode and the kernel mode, but the kernel mode are separated from different parts, like process communication, memory management, and the CPU scheduling are from different parts. They separate them. It's a microkernel. Microkernel is good design or bad design? It sacrifices the efficiency, right? Different, but need to communication. The communication takes time. But the good thing is separate them is easy to maintain and easy to development. So the modern operating system more care about how can we manage well, reduce the bugs, extension, not only consider about the efficiency. So this is the microkernel. Benefits, okay, easy to extend to a microkernel, easy to port to operating system to a new architecture, and more reliable and more secure. Okay, let's finish this part. Let's take a break. Okay, take a break, 10 minutes, we come back. Yes, so I stop this.
It's okay if you keep on sharing. I think I emailed you a poster to show up on the board. That's okay. In
Hey.
my email.
Both.